Hi, Susan. Can you hear me?
Yep. Can you hear me?
Yeah, sure.
Perfect.
Hi. So please let me give a brief introduction to the Professor Susan Athey. Susan Athey is the Economics of Technology professor at Stanford Graduate School of Business. She also serves as a long-term advisor to the British Columbia Ministry of Forests, the founding director of Global Capital Social Impact Lab at Stanford Graduate School of Business, and associate director of the Stanford Institute for Human-Centered Artificial Intelligence. Welcome, Susan.
Thanks so much. Go ahead.
Yeah, you can start whenever you want.
Great. Thank you so much for having me here. Let me just share my screen. Wonderful. So today I'm going to start out by talking about some recent work I've been doing on stable machine learning, joint with Ping Kui, and thanks for inviting me here, and several co-authors. And then if I have time, I'll try to step back and give a little bit of a bigger picture about how economists have been using machine learning and causal inference combined in recent years, which basically, as of about 10 years ago, most economists and social scientists knew very little about machine learning, and now there's a very active field combining it in applications. So I think, some folks have already made similar comments, but I think it's still really important to start by just saying a grounding about in the last few years, we've seen a lot of criticisms and challenges faced by machine learning models. And we've seen challenges in their application and people questioning them for all sorts of reasons. They're not interpretable, they may not be stable or robust, models may not be transferable, and people are worried about issues like fairness and non-discrimination. And there's also a concern that AI is not achieving its potential to be sort of human-like. And all of these challenges come up both in in science, but also in practice. So I work with a lot of firms. I'm on the board of a number of tech companies, and one of the common challenges they have is they hire young machine learning people who come in and want to use new models for old problems, but they have trouble kind of fitting in with the business objectives. So just imagine, for example, before COVID-19, if you were using a complex black box machine learning model for credit scoring, and then COVID hits and somebody comes and asks, well, how is our model going to do? What are its weaknesses going to be? And it might be pretty difficult to even understand what's going to be wrong with your model. While in the old world, people would have estimated a simple logistic regression with, several covariates in it. They might have been able to understand that, say, the coefficient on restaurants might change after COVID-19, and they might be able to reason about where their model might go wrong. On the other hand, all the models will go wrong, and the simple linear model might go wrong in ways that are also hard to understand. Just because you can look at a simple model doesn't mean that its behavior is easy to understand. And in particular, the coefficients in a simple linear model actually depend deeply on the joint distribution of all the covariates. And that's, it can be the simplicity of the model and from inspection doesn't necessarily correspond to a model where you can understand what will happen if the world changes. Now, what causal inference is about is really learning a model of how the world works. And in the parts of causal inference that I work in, like economics and biostatistics and so on, one of the main things we try to do is estimate causal effects. So we think we might understand how the world works, but we just want to estimate the magnitude of the effect of changing a variable. And if we understand how the world works, then we've got a good starting point, and that's just what came up in the last seminar. You can, of course, in the old world, with small data sets, we used to mainly focus on just learning an average effect of one intervention. At least in economics, we would think about what happens if you raise price, what happens if you give somebody a drug. And we would look at the average effect for a population. More recently, machine learning has been helping us understand more context-specific impacts of interventions and what we call heterogeneous treatment effects, and that's something I've worked a lot on. If you have a model that maps context and interventions to outcomes, then you can apply that model, and it is more likely to be stable, interpretable, and transferable. If you understand the relationship between a context and a treatment effect, then it's very easy to just reweight your model for a new context distribution. And in terms of fairness, many aspects of discrimination also relate to correlation versus causation. You know, your performance might depend on your physical and mental ability or psychological factors. And gender and race might be correlated with factors that shift these distributions, but have relatively limited, if any, direct causal effects. But if you just put everything into a big predictive model, a parsimonious model that uses race and gender can have better mean squared error if the true factors are mismeasured or hard to observe. And so we end up with unfair models, not because the true data generating process requires us to understand race and gender, but just because a regularized model will load up on them in a context where you have less data or other types of mismeasurement. So when we go to think about these ideas in prediction, we can see them showing up in even something like image classification. So if we start from training data that, say, has a lot of dogs in grassy areas because it comes from some particular distribution, then a predictive model might decide that grass is an important predictor of dogs, even though in principle, a grass is not an inherent feature of a dog, but it happens to be correlated with dogs in the data set that you started with. But then if you go to a data set with different context, maybe you have data from a city or data from dogs in different settings, you might make mistakes in terms of prediction. So, in principle, this wouldn't happen if you had, large enough data sets. Of course, in your training data with large enough data sets, you would learn that there are some dogs that aren't on grass and that there are some other animals that are on grass, and you would, eventually figure out what's important about dogs. But in, medium-sized data sets where you've just, done a black box feature generation, and feature selection, you may make those mistakes. And so one way to think about, where this is coming from is just that there's what we would call a spurious correlation, and which can be formally defined, but just in general, we've got something that's showing up alongside of dogs in one situation, but won't always have a relationship to the classification of the image as a dog. So how to attack this problem? Well, there's a variety of different ways. One, we have to narrow down the problem in order to make progress. And so a couple of papers that we've written have focused on the idea that the joint distribution of features might be the thing that's shifting across an environment. So if we want to ask to have a stable model, what we can translate that into a model that's going to work well when the joint distribution of covariates changes, but where there's more stability in the underlying data generating process in terms of the relationship between X and Y. So the mapping from X to Y is stable, but the joint distribution of the X's can change. So that's a general concept, but we then want to specialize it further and think about, okay, well, if the joint distribution of X is changing and something's stable, what are the mistakes that you could make? And so we separate the X's into two types of features, what we call the stable, or they could also be thought of as causal features, which are the things that do have an invariant relationship with the outcome, and then other types of unstable features. And there's a variety of different assumptions you could make, which you can then operationalize into algorithms that exploit them. One of the ones we look at in our papers is an assumption that the true data generating process has the property that the expectation of Y given the stable and unstable features is equal to the conditional expectation of Y given S. And so that's basically just saying that the stable features are a sufficient statistic for the outcome. And so then you might ask, well, if that's the case, shouldn't machine learning just directly learn this relationship? But the problem is that even if we have the data generating process I've written, there's a variety of reasons why other features might be correlated with the outcome unconditionally, and they might also be correlated with stable features. And there's a variety of ways that can happen, underlying data generating processes that lead to that. But that plus other problems can make the predictive models perform poorly. So in particular, anytime you have a smaller data set, you're going to have to make trade-offs about your functional form. And generally, there'll be some regularization going on and necessary misspecification. So if you don't have enough data to perfectly learn the functional form, then your predictions will in general depend on the covariance of the stable and the stable and unstable features. And generally they'll depend on the joint distribution of all of the features. And so it's this sort of real world setting where you have misspecification that we start to get into problems, but we also can potentially have methods that fix the problems. And in particular, methods from causal inference under unconfoundedness have been designed to attempt to isolate the effect of each feature. And although the methods weren't originally phrased that way, one way to think about them is that they reweight your data distributions so that covariates are uncorrelated with the treatment. And these methods were designed to control for confounders. Confounders are things that affect both an outcome and a treatment. But what they do in practice is they say, well, in the data, we might see a situation where it's different types of people are getting a treatment than aren't getting a treatment. And so in order to estimate the causal effect of something, you reweight the data so that in the reweighted data, you have the same types of people getting the treatment and not getting the treatment. Now, what this type of approach is going to do is it increases the variance in prediction. So trying to estimate a causal effect, estimate the magnitude of the effect of an intervention using these types of methods will make your predictions worse. And that's something that we've always done in economics and biostatistics when trying to estimate a treatment effect. If we have observational data, the methods we use hurt our ability to predict, but they help our ability to estimate an important parameter of the model, which is the treatment effect. And so a lot of these methods are actually focused on trying to get an unbiased estimate of a treatment effect rather than reducing the variance of prediction. They don't make a bias variance trade-off in prediction. Instead, they optimize for unbiased estimates of treatment effects. But if what we're trying to do is uncover a true causal relationship and therefore accurately assess that these unstable features are not important for predicting outcomes, optimizing for an unbiased estimate rather than for a bias to resolve a bias variance trade-off is exactly what you want to do. So if we go forward on that, if we just had a small number of covariates, we already know how to do this. There's a large literature with lots of different methods proposed, including those that bring in machine learning to estimate nuisance parameters. This large literature on unbiased estimates of causal effects when you have a small number of treatments. And again, what we've been publishing a lot of papers on in the last few years are advances that allow you to have a large number of observed confounders. So you're in a situation there where there's a small number of target parameters of interest, like a treatment effect parameter, and you have lots of variables that might affect both treatment assignment and outcomes. And we call those nuisance variables or nuisance parameters. And we use machine learning to estimate the nuisance parameters, things like propensity scores and outcome models. And then, but then pull those together to target an unbiased estimate of a single parameter, which is a treatment effect. So we know how to do that already. And there's, again, hundreds of thousands of papers written about this in the small data setting, and tens of thousands of papers written about it even in the big data setting. If your problem is to estimate the causal effect of a small number of treatments. What the machine learning literature has gotten amazing at is doing prediction with many features and using regularization and cross-validation and various types of tuning to balance bias and variance. The methods that we propose for stable prediction are really designed to reduce the dependence of our predictions on the joint distribution of covariates. And they're thus more stable, but they're gonna reduce the bias in our estimate of the true underlying data generating process, but they're going to have the trade-off that they're going to increase variance. So they may not minimize mean squared error in a particular data set. They generally won't. What they're going to be good at is being stable across different data sets. So in a pair of papers, one in AAAI and one in KDD, both led by our former student, Kun Kwang, we propose methods that are that are inspired by causal inference methods in order to and what we do is we find weights, we reweight the data to balance the distribution of covariates between treatment and control, imagining that each of our covariates is a hypothetical treatment. So the standard literature would have just zeroed in on one treatment and reweighted just based on that one treatment. But what we're going to do is find weights that essentially think of the whole covariate vector as potential treatments. Now, again, if we had huge data sets relative to the size of our covariate space, we could do this exactly. And this would really be equivalent to, if you had binary covariates, it would just be equivalent to running an ordinary least squares regression. But in large data sets, we might have more covariates and observations, or we might not be able to well estimate such an ordinary least squares regression. So our methods can be thought of as an alternative to like a lasso or a ridge for running regression when you have lots of covariates. But instead of optimizing for mean squared error of prediction, like you would in a standard lasso or ridge, we're going to be instead introducing more bias and more variance and less bias to try to really isolate the effects of covariates rather than learn from their joint distribution, which we think might not be stable. So the first paper focuses on binary covariates. The second paper tackles the sort of harder learning problem where you have continuous covariates and you need to make further approximations. So of course, in the papers do a variety of experiments. Over on the right, I'm showing an example where we look at different models, and in the models on the left side of the chart, we have distributions that are more different than the training data, while on the right side, our test distributions are closer to the training data. And there we're seeing, as expected, that other types of regression models are doing better when the test data is close to the training data, because they're optimized for mean squared error, whereas our model is going to do better across a wider range of test distributions. So I've recently applied these to a large scale industry application. We haven't actually published this yet, in part because of data issues with the data is proprietary. But we've shared the results, so I'll just give these to you as a nice real world setting that was faced by a real firm. They were trying to do fraud detection. This is a large payment provider in the US, and their data had features of buyers, people who were going to make a payment, and the training data has a fraud tag as to whether this transaction turns out to be fraudulent. And we had samples from millions of transactions and 625 features, and they were trying to come up with a better fraud model. And of course, the world of fraud, things are always changing. So they were very concerned about stability. So in order to assess stability, we did two different methods for making the test data different than the training data. And I should say, this is one of the parts that's the most unsatisfying about this whole stability literature, is if you want to test your model, you have to test it in different environments, but it leaves a lot of discretion to the analysts to define what different environments you're thinking about. And of course, if you knew what all those different environments were, then you could just optimize for those environments. So you're kind of trying to tie a hand behind your back and train a model in a way that's not knowing what these test sets will be, but still the researcher has to find some way to generate realistic test sets. So in this case, one of the things we did is we used training data from transactions before the US holiday of Thanksgiving, and we used test data for transactions after Thanksgiving. And in a second example, we used the existing buyer subsegments that the e-commerce firm had defined. We used training data from 3 of the buyer subsegments, and then test data from a 4th subsegment. And so you can look at the data set sizes we have here. In each case, we had hundreds of thousands of training observations, and tens of thousands, or in some cases, hundreds of thousands of test observations as well, depending on the segments. Now, one of the challenges we had here is that the stable learning model that we proposed in our previous papers doesn't scale really well. And so in this project with my graduate student, Rohan Zan, what we did is we used batch learning and came up with a way to make it computationally feasible, even with a large data set. So here are our results looking at the logistic loss from fraud prediction when we evaluate them on the test sets I described earlier. So we find across all of these different cases that since our test set doesn't look like our training set, our balanced model is going to do better in terms of mean squared error on the test set, and thus is more generalizable. And so, I was very heartened by doing this example because this was really a realistic setting, and we did really treat it as a black box. We didn't do a lot of feature engineering. We just threw in all the features that hundreds of features they were using in the model. This was we were comparing to the kinds of models they would use in production at this large firm. and the stable learning model did better with kinds of realistic distribution shifts. So, going forward, there's still, a fair bit to do. There's a lot that's kind of ad hoc about the approaches we've done, and they also are going to work well under certain kinds of circumstances. But there's certain types of ways that spurious correlations can arise where these methods, might not do as well for, and it can be really helpful to, when you do your feature engineering for these models, to be careful about what kinds of features you throw in there. For example, you would be typically, in applications, you wouldn't throw in features that come after your outcome is realized in the training data. Generally in practice, if you're predicting fraud, you're going to get variables that you knew before the fraud was realized. But if you just took all the data and mixed it all up and didn't pay attention to timing, you could end up making things worse with this type of stable learning model. But so there is some care that needs to be taken when you're throwing in things into this black box model about to rule out certain scenarios where adding covariates can make things worse. Okay. So I just have a couple minutes left. I just want to say a couple of things for those of you who aren't familiar with how causal inference is used in practice. And just to clarify, I should go to 10:35, right? Tell me if I've got the timing wrong. Is that right, Eli?
You can.
Or should I stop? Should I stop now? I forget.
No. You may have 5 minutes for the video and maybe 5
for questions.
Yeah.
Perfect. Just want to make sure I remember the timing right. Okay. So in seeing the way that machine learning has been coming into causal inference in economics, we have really two big strands of work in the social sciences. One is what we call program evaluation or treatment effect estimation, and that's partly what I've been talking about already. In that case, the estimands, we're not trying to predict, we're trying to estimate something. We're trying to estimate average effects. We're trying to estimate heterogeneous treatment effects, or we're trying to estimate optimal treatment assignment policies. But the common theme is that our treatments are typically low dimensional. A binary treatment is the most common application. We might have a single continuous treatment, something like price. And then a lot of the literature is around what is it in the data that allows us to actually estimate this simple parameter. And we look at things like randomized experiments, natural experiments, what we call regression discontinuity, where you make use of treatments being different when you cross a boundary, like school district boundaries, or we make use of the fact that you only get entered into a program if your test score crosses the threshold. Longitudinal or panel data, where you can learn about a person's latence over time and thus get rid of various kinds of selection and confounding problems. We work on problems where there's treatment in networks. So the focus of the methods literature is to find the best methods for each different kind of setting where it's possible that you could estimate causal effects. And there's a certain fairly short list of things that actually show up regularly in practice. And so a lot of the research has been optimized around these commonly arising settings. It's very common to observe states or counties over time, or to observe workers over time in administrative data. It's very common for there to be these kinds of thresholds used for people to get access to government programs. So there's a lot of interest in a fairly small number of methods for causal inference. Where the recent advances from machine learning have been about estimating heterogeneous treatment effects and trying to use those estimates to do targeted treatment assignment policies. And here I've just put up an example from a paper that I worked on where there was a randomized experiment nudging people to apply for financial aid at the City University of New York with tens of thousands of people. And here we wanted to contrast the performance of a predictive model versus one that was optimized for estimating causal effects. So if you used a predictive model to predict which people were not going to fill out forms, the predictive performance, that's the baseline here, if you allocated people according to predictions, so just the people who you thought wouldn't fill out the form were the people you assigned to treatment, you actually did worse than if you randomly assigned the treatments. On the other hand, if you assign people to the treatment on the basis of a conditional average treatment effect, you did better than random assignment for treatment. And so here we have the x-axis is the percent treatment, and the y-axis is the share of people who fill out the forms. And as we vary the percent treated, this green line where you assign based on conditional average treatment effects is better than random assignment, the purple line, and better than assigning just on the basis of who was predicted not to fill out the forms. Now, if you don't have an experiment, then you're kind of stuck with predictions for allocation. But here we're showing that if you predict the wrong thing, you can actually do poorly in targeting treatment. Well, in this case, actually, it turned out that there was a set of people that was identifiable on the basis of their covariates who, if you had data from a randomized experiment, you could in fact determine that those people were more sensitive to nudges. And they actually turned out to be people who were already pretty likely to turn in their forms. You were kind of nudging them over the edge. So that's one strand of the research. Another strand of the research, which is more close to the generative models and Bayesian modeling in machine learning, is what we call structural estimation, where we estimate the parameters of generative models and do counterfactuals. So we ask what would happen to firm demand if price increases. And the goal is often to estimate the impact on welfare or profits in our alternative counterfactual regimes, including regimes that have never been observed before. So sometimes machine learning people say, how could you do counterfactual on a regime that's never been observed before? And the way that we do that is we try to actually estimate the preferences of agents. And then we can use a behavioral assumption where we assume that, say, consumers maximize utility or firms maximize profits. And if you understand the preferences of those agents and you understand their objectives, you can predict how they'll respond in different settings. So I've done this a lot with timber auctions and search advertising auctions. Models that can be a little simpler to understand would be discrete choice models from, that's the simplest kind of structural model that is very popular in economics and marketing. There we assume that consumers maximize utility. Dan McFadden won the Nobel Prize for work he did in the early 1970s, showing that if consumers maximize utility, and the errors in their utilities are extreme value, type 1 extreme value distribution or Gumbel distributions, then the predicted probabilities from a model where consumers maximize utility take the multinomial choice functional form. And what that means is that if you estimate a multinomial choice model to fit consumer choice data among different products with different prices, the parameter estimates can be interpreted as the parameters of a consumer's utility function. And so that means you can interpret what you learn from a multinomial choice model as a generative model of consumer preferences. And then we use these models to assess what would happen if two firms merge, or what would happen if a firm raised its price to something they hadn't raised before. I worked with David Bly and Fran Ruiz and Rob Donnelly in some papers, and more recently with Ayush Kanodia, to specialize these models to bring in matrix factorization techniques from machine learning. And in our papers, we show a variety of ways in which our models do better, and particularly when they do well out of sample in scenarios where prices change. So I run out of time, so I won't be able to explain all the off-policy evaluation type things we use, but the general theme of it is that we estimate models that are really focused on understanding how consumers respond to price changes. So in this type of model, there's a preference parameter for utility on a price. And then we show that our model does well by looking at different types of off-policy evaluation, or look at predictive fit on days where prices change, and show that our model performs well. Once you do that, then you can do things like target coupons and so on. So that's kind of what we've been doing in economics. And I do think, you know, these types of generative models can combine machine learning in the predictive components of the model while still retaining a lot of the tricks we've used historically for targeting parameters that are really important to get right, like in this case, the effective price. All right, so I'll stop there. Thank you.
Thanks, Susan, for this insightful talk. Maybe we can have one questions from the audience. So if you have any questions, you can use the chat box or just raise your hand. Okay, let's wait. Is there any questions from the audience? Maybe I have a very quick question. Since you know that you come from the business school, so maybe you have some different background from us from the vision. So I'm interested in that you have introduced some the applications of the causalities in some real world problems. Maybe I want to know if you have some ideas about how causalities are used in some industry problems.
Yeah, well, so the examples that I just looked at, I mean, there's a lot of firms right now trying to understand how to set prices, how to target coupons, how to target ads. And of course, I think the machine learning community often thinks that they've already solved that problem because their models are used in production for those types of problems, but they're typically used in a predictive way. So, you know, you tell Facebook, you know, target my ad to who clicks, that's a prediction problem. But that's not what an advertiser wants. When an advertiser puts up their ad, they don't want to target who's going to click on the ad. They want to target the people for whom the ad is going to make them purchase when they wouldn't have purchased before. So if you're a travel firm, and I'm on the board of one of those, if you put an ad on Facebook for your travel firm, the people who click might be just people who already have a trip booked with you, and the ad reminds them to come and check on their reservation. So it doesn't cause a sale, but the people who've already booked may be more likely to click than the people who haven't booked. So a predictive model doesn't target the right object. But the reason that so many firms, you know, it gets you part of the way there. Like if you're not going to click, then probably the ad is not effective. So if you rule out the people who won't click, you know, that can get you part of the way there. But then within the people who might click, you really want to focus on the people for whom your ad is going to get a new purchase, not the people who already purchased. So those are the settings where firms are now, they got the big win early on with the black box model, but now they need to go back and rebuild those models to optimize for treatment effects if they want to get even better improvement. So you're seeing a lot of firms hiring people who are experts in causal inference, not in the first stage when you're just getting the data up and you're just trying to get some kind of basic model, but the causal inference really helps you get from 80% performance to 90% performance, or it helps you, you know, when you're trying to do better than just, you know, a crude measure. And it's the same for setting prices. If you look at historical data in supermarkets, you know, prices change around holidays. You know, prices in historical data changed for a lot of reasons. So it's important, if you want to really understand the causal effect of price, to use more tailored techniques. And one of the reasons economists got focused on causality and estimation to start with is that almost every data set you look at, prices and quantities are positively correlated because firms raise prices when demand is high. So you get this crazy thing that would say, oh gosh, if I raise price, I'll sell more stuff, which is almost never true. So causal inference has really been tailored for those kinds of settings where you get nonsense answers out of a pure prediction model, and you really need to focus on understanding the domain to get a more sensible answer.
Yeah, thank you. Very interesting. There's a question from the audience. Maybe could you please give a very quick answer to this?
Yeah, so one of the challenges actually economists have is that a lot of the really interesting data sets are proprietary. So I think, we're doing better at getting a few data sets available that people can work on to answer these economic questions, the same way you do in machine learning, where you have these great, awesome open data sets so everybody can agree on where they should be targeting their models. But we have long panel discussions at many conferences how it's actually unfair of researchers like me at Stanford have all these data access and companies give us their data proprietary, but it's not openly available to everyone.
Okay. I think we have no time for more questions. So thank you, Susan, Dan, for joining us today for this insightful talk and some comments. Thank you very much.